Okay. So I'm recording now. Let me start the presentation and share the slides with you. The slides are roughly what they are on the ones posted on the syllabus, so you can consult them. But I'm making some changes here and there. Okay, now it should be shared. So we are starting a new segment, sequences, summations, recurrence, relations, and eventually proofs by induction. In recurrence relation, you will start seeing the first guise of something called recursion, which basically is the main topic of this chapter. Okay, it's a simple concept, but at the same time, it sort of gives you, quite often a pause, and the aim is to just familiarize ourselves with recursion in many guises: recursive sequences, recursive data structures, recursive algorithms, and a way about thinking about recursive processes. For example, induction is a way to argue if you have a recursive definition in your hand or a recursive algorithm, how do you reason about its correctness, about its efficiency? So that will be the topic basically of chapter 8. But in the meantime, in the process, we'll define a lot of terms that are useful in general, and also specifically useful for these concepts. So we start with something that actually is just another guise of something we defined last time: sequence. Remember, we talked about sets and we talked about Cartesian products, which were ordered which were elements of Cartesian products, which are ordered sequences, with ordered tuples, which are basically sequences. And we looked at them as sequences, and we looked at them as strings over some alphabet. And now we'll be looking at them as sequences. So, but we'll yet put another lens on a sequence, on the term sequence, because we'll define a sequence to be a function, a special type of function whose domain. So somebody asked, when will the practice test be uploaded? I'm not sure, because I would like to check that problems are sort of, the first thing is that I'm not sure how much material, when will we, how much we will cover this week. So therefore, I want to test first the practice test that it doesn't include stuff that I don't think we'll likely to cover, and then we'll release it. So think like end of this week. That's for the people who cannot read chat and view this later. That was an answer to the question: we will have a practice test, and when will we post it? Okay, so it says a sequence is a special function whose domain is consecutive integers. Okay, why? So, for example, a sequence of heights of a person, who is growing. So h0 is the height at when the person is born. Let's say it's 20 inch. Then a year after is 30 inch, 34, 37, 40, 43. Okay, the first 6 years of height measurement of some human. You can view this as a function that assigns to consecutive integers 0, 1, 2, 3, 4, 5 values in integer values, right? The inch rounded up. So that's another way of viewing a sequence. The domain in this case are consecutive integers from 0 to 5, and the range is integers because we're running. I mean, it could be also naturals, right? Because nobody has a negative height. And before, we looked at the sequences as elements in a Cartesian product of, from this view, what would be the range of the function, right? So the height sequence is a 6-tuple of integers. And viewed in this way, these integers are values of this function on these consecutive integers, right? It's just squeezing your eyes differently. You can look at this sequence as that implicitly it's a function that's assigned to 6 consecutive integers, these 6 values, 20, 30, 34, 37, 40, 43. Or you can think of this as, as just a 6-tuple in integers, right? It's equivalent. So this, recall this notation, right? That, because we will be using it all the time. So this stands for a Cartesian product of integer with itself 6 times. In other words, a set of 6 tuples whose every element is an integer. In other words, things that look like this, where each of these HIs is an element of integers. So a finite sequence has a finite domain. In other words, if you have a sequence of 6 integers, it's a function that takes 6 consecutive integers as its domain. But you can have an infinite sequence. For example, powers of 2. The first element is 2 to the 0, 1. Second element 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, etc. This defines a sequence whose a function. So this infinite sequence is defined by it's a function whose domain is all non-negative, or positive integers, right? So the first element is 1, then there is 2, 3, 4. These are the domain elements, the arguments of the function, and the values of the function are integers, right? And the function has a closed formula. H of I is 2 to the I minus 1, right? So here is an example of a sequence defined that the first these things here are called indices. So this is a value of sequence H at index 0, value of sequence H at index 1. This sequence is defined as if the first index is 0. This one is defined so the first index is 1. These are arbitrary choices. They're all okay. You can define sequences. It's up to you what the starting index is. Typically, the starting indices are either 0 or 1, but in some application, it might be convenient to denote the starting index with something with some other integer. So these are only customary initial indexes. And you have to be aware that a notion of a sequence is that it starts at some index and it's either infinite or it stops at some other index higher. But the beginning is an arbitrary one, and it's up to you. How do you specify a sequence? Okay, well, one way is to just list its values. right? Like this height sequence of somebody growing, or average rainfall in California since 1950. So it will be a sequence of 71 or 72 elements, depending how you count. And by the way, the natural first index might not be 0 or 1, but 1950, right? So let's say you denote the rainfall as Ri, right? In year I, the rainfall is Ri. And that sequence starts, the first element is R of 1950, and the last one is R of 2020. Or say average weight of people by age, right? So that one would start at year 1 and, sadly end at some index. Option 2. We can also give an explicit formula for the sequence because a sequence is a function. So, for example, here is a closed formula. The nth index of sequence f, so in other words, the term fn of the sequence is defined as 2 to the n plus 2 times n. And we say, let's say that the initial index is 1. This defines an infinite sequence. So for the first element, we're told has index n equal 1. So the first element of the sequence is f1. And then we use this formula to compute what's its value. 2 to the 1 plus 2, that's 4. Now the second element, we plug in n equal 2 to this formula. So this gives us 4, and this gives us 4. So it's 8, right? If we plug in n equal 3, we're getting 8 here and 6 here. So 14, etc. This is so-called closed formula because it's called closed because we can evaluate it. It's just a function of n. So for any n, give me any n. Let's say you say, okay, my n is 100. I can evaluate what this formula is for n equal 100. So here are some examples of infinite sequences. So let's say sequence H, its domain is Z plus. So the first index is 1. And the function is an identity. Okay, so to every index, the value of the sequence at that index is just the index itself. So this is the sequence. Right, it's simply the sequence of integers, of positive integers. Now let's say this is the closed formula that defines the value of the function. So it's 2 over the index. So okay, so let's look at this guy. This is G1. It's because the first index is 1. G1 is, okay, let's plug x equal 1 to this formula. It's 2 over 1. So that's 2. This is G2. That's for index x equal 2. So 2 over 2 is 1, hence 1 is the value. And right, so the consecutive values are 2 over the index. So the third element is 2 over 3, the fourth is 2 over 4, the fifth is 2 over 5, etc. They're all reals. In fact, they are rationals, right? But they're members of this domain. You can also define a constant function. This will define this kind of boring sequence of infinite number of 3s, right? Like, so it's just a sequence of 3s. Okay. Not a complicated sequence, but you might use it in some application. So range is any set, right? So it's the domain of the function that makes it a sequence. It has to be consecutive integers. The range is whatever. So for example, if the range is reals, then we're talking about infinite sequences whose elements are real numbers. Here, this G is some infinite sequence whose elements are integers. You can also have sequences of bits. right? Or bit strings, if you define the range as 0, 1, 2, for example, power 8, the range would be 8-bit strings. So at every index, you have some 8-bit string, right? Okay, so this is a definition of a sequence by a closed formula. I had some examples so far. But here is a recursive definition of a sequence. And that the notion of recursion in that particular instance has a special name. It's called a recurrence relation. So a recurrence relation contains two things. First of all, you define some initial values of a sequence by just saying what they are, okay? And separately, you have so-called recursive rule, which defines, so after some threshold, okay, in this case 2, you don't list the values of the sequence by hand. Instead, you define them using this formula, which is a recursive formula, because it defines the nth element of the sequence as some function of previous elements of the same sequence. In this particular case, it defines the nth element as a sum of n minus first element and an n minus second element. Let's see how that works. So here is it's a famous sequence of Fibonacci, a mathematician from I think 18th century, although I'm not sure. I think I have that date somewhere on the slide, but I already forgot. So it's Fibonacci sequence is defined by two first terms. There's the first and the second term, okay, with index 0 and index 1, and they're both 1. And after that, the sequence, the nth element of the sequence is defined as the sum of the elements of the same sequence at position one earlier position and 2 earlier positions. Okay, so for example, if I want to say, okay, what is this formula? How does it define the second element of the sequence, right? Because I have this zeros and the first already defined. Well, so I plug in this recurrence relation for the case of n equal 2. This is n minus 1 is therefore 1. N minus 2 is 0 because n is 2. But I know what these guys are. This is 1 by the base case, and this is also 1 by the base case. So this is just 1 plus 1, which is 2. Okay. Now for the third element of the sequence, so now n is 3. So here n minus 1 is 2. So therefore, this f3 is f2 plus f1. That's written here. And if I plug in the values, right, I know f2 is 2, f1 is 1. So it's 2 plus 1, which is 3. The next one, f4, is a sum of two previous ones, meaning f3 and f2. Now I just look up. f3 was 3, f2 was 2, so it's 3 plus 2, 5. You can see that this formula actually does something kind of interesting, right? Like at the beginning, it was a constant. Then it looks like, okay, you're just looking at consecutive numbers, but actually you have a jump now, and you will have bigger jumps. F5 is the general formula, right? Obviously, 5 is greater or equal to 2, so you have to define it using this formula. So F5 is F4 plus F3. I know that F4 is 5, F3 is 3, so it's 5 plus 3, which is 8. F6 is F5 plus F4, 8 plus 5, 13, etc. if you write out this sequence, I mean, you can really see, okay, this guy is the sum of the previous two, so it's 2. This guy is the sum of the previous two, so it's 2 plus 1. This guy is the sum of the previous two, 2 plus 3, 5. This guy is the sum of the previous two, 3 plus 5, 8, etc. Right? So 30, this guy must be a sum of the previous two. 13 plus 21 is 34. This function grows faster and faster. It has a very simple definition and not so simple behavior, right? Okay, let's see, and that is also indicative of the power of recursion. It seems like not so easy to see, okay, what is that, if I try to have a closed formula for what these values are, it looks like it might be a complicated closed formula. If it exists, it does, and you'll see it in a few slides. But it doesn't look like it's going to be simple. This is as simple as it gets, right? This recursive formula, and yet it generates a rather complicated object. Here is another example. Let's say you have a base case is just a single value. I define the first element of the sequence as 0. And then for any index after that, so starting with 1, I define subsequent values of sequence G as follows, using the following recurrence relation. The nth element is equal to 1 plus the element given at the index, which is half of n. Because what's n division 2? That's an integer division of n over 2. So it's a n over 2 floor, right? The floor and ceiling functions, if you haven't still read, please do. It's in the function section. And you have to know what this stands for, right? Which is just floor, the closest integer value, but that is not greater than an input argument. Let's see how this behaves. So what's the first element? Well, it's what's a half of 1? 1/2 floored, it's a 0. So it's the 0th element plus 1, right? Because for n equal 1, this expression is a 0. Okay, so it's the first element plus incremented, so it's 1. What about the second element? Okay, so now it's 2 divided by 2, so that's a 1. Okay, so the recursive formula is that the second guy is the first incremented. The first is a 1, so we stick 1 here and we increment it, it's 2. The third element, well, what's here? For n equal to 3. It's 3 over 2 floored. Well, that's a 1, right? Because 3/2 floored is a 1. So we already know what this expression is. It's the same as here, so it's a 2. What about D4 and D5 are about basically, I don't have to compute them separately, because if I take 4 over 2 floored, I get the 2. And if I take 5 over 2 floored, I also get the 2. Basically, it works like this for every integer. If even integer divided by 2 and floored is the same as that integer plus 1 divided by 2 and floored. So these pairs of values, G2, G3, G4, G5, will be the same always. Okay, so it's a G2 plus 1. G2 is 2, so these guys are equal to 3. But the next two guys are also equal to 3, because 6 over 2 is 3, and G3 was 2. So now the fact that these two are the same basically means that the next batch of 4 are the same, right? Because pairwise, even and even plus 1 are always going to map to the same thing. But because these two guys were now, these two pair of elements are defined in terms of consecutive values earlier, and these consecutive values indices corresponded to same values, now this equality implies this one. So then the next, what does this mean? This means that the next batch of 8 values will be all equal to 4. And then the next 16 values will be all equal to 5. Okay, so okay, perhaps you can see this now, but this is a very concise way of describing these relations. And it takes some thinking to reconstruct what does this imply, okay, in terms of the exact values of this function. So you can think of a recurrence relation as a very concise, economic way of describing a behavior of a sequence that is infinite and might have complex behavior in terms of its real values. And yet it's all encoded in this very tiny formula, recursive formula. Okay, another example. You define the first two terms of a sequence. The first element is 2, the second element is 4. And after that, all elements with index n are defined through a recurrence relation as sort of reminiscent of Fibonacci recurrence relation, but instead of just adding the previous term and the one before, I take the previous term and I multiply this by the value of this index, and I add that to the value of the sequence, 2 indices to the left. You might have a general question: how many base values do you need to define so that the combination of base values and recurrence relation together define a sequence? Well, it depends on the recurrence relation, and in here, 2 values suffice because nth value is defined in terms of 2 previous ones. So these 2 guys will suffice to define the second. And now that you have first and second, that's enough to define the third. And if you have third and fourth, second and third, that's enough to define the fourth, etc. So let's look for n equal to h2 is 2 times h1 plus h0. So it's this formula 10. For n equal to 3, this is 3 times h2 plus h1. h2 was 10. So I'm plugging these values, 10 for h2 and 4 for h1, and I get it, right? So I can evaluate. It's the same recurrence relation, it's just for different n. So this will be always 1 less this index, and this will be 2 less than this index. And then I just look up the previous values to compute. Clearly, this function explodes like way faster than a Fibonacci because I'm not just adding the previous term, but I'm multiplying it by the index. Okay, let's say you have a recursive formula like this. The j plus first element of the sequence is defined in terms of previous 3, in terms of the jth, j minus first, and j minus second. And how many initial terms do you need for this recurrence relation to successfully define the value of sequence h? at any index. And the answer is that if the recurrence relation defines the next value in terms of consecutive values of the sequence at consecutive indices, and it's the previous 3 indices, then you need 3 initial values to be defined for this little piece of code to be able to recursively define all values of the sequence for all indices. So here, this recurrence relation is a special case where k equals 3. So 3 initial values suffice. So for example, h, well, the first guy is 0, the second is 3, the third is 5. And they suffice to define all the others, right? Like just plug in the formula. So you have to be careful with the indices. You know, here was a case of a recursive formula where the index of the new element is on some variable, and the previous elements are basically that variable minus something. But that's not even general enough, right? Because in this case, the previous one is not n minus anything; it's n divided by 2. But here the new guy does not have, you know, this would be the n, then this would be n minus 1, n minus 2, and n minus 3. But there is nothing that says, okay, every recurrence relation has to have this form. You know, I can have different guises of recurrence relations. They're all recurrence relations. This is another example. So don't be stuck on that, okay, this index somehow looks different. What's essential about this is that these indices are all smaller than this one, okay? If you have the case like this, that on the right-hand side, it's some formula involving values of the sequence at some indices which are smaller than this one, any formula like this is a case of a recurrence relation. Okay, so here, if I define the first 3 elements of the sequence by hand, this is the base case of the recurrence relation of the definition of the sequence. Then this suffices to define all the others. In particular, let's see how it defines the H3. How do you define H3? Well, you have to instantiate this with j equal 2, right? At which point this becomes 3. If j equals 2, this is 3, and this is 2, so it's here. This is 2 times H1, it's here, minus 3 times H, this is j minus 2, j is 3, so this is, sorry, j is 2, so this is a 0, right? So each of these is defined by the base case, so I just stick them in, and I have this formula, right? So somebody asks on the chat if it's okay to basically change the variables. Yes, so you can, if you feel like it, you can re-represent this recurrence relation in terms of call this n, in which case this becomes n minus 1, this becomes n minus 2, and this becomes n minus 3. Okay, it's the same. It didn't mess anything. It didn't make any change. Okay, if it's convenient for you, you're welcome to do such change of variable move. So if I want to define H4, right, I have to instantiate for j equals 3, at which point my formula becomes this. I have already all these values. I stick them in, I compute, right? I have some funny behavior, as you can see. these guys grew, then the next one grew quite a lot, and the one after that, it kind of, grew just a little bit. How would this formula behave in general afterwards? Okay, why are we talking about these recurrent relations? These formulas are, they capture in a dynamic systems, like population growth. A value of the population, I mean, the number at this point is some function of previous numbers and some environmental factors, right? Finance, another kinds of dynamic system. In biology, this dynamism, the value of the system at some point is some function of previous states of the system that that basically describes. You can use it to describe behavior of a cell, behavior of any biological system, or a mechanical system. But it's also in computer algorithms. An algorithm on some inputs might include making a recursive call to the same algorithm on modified inputs. And therefore, some aspect of how the algorithm behaves on input, let's say n, perhaps is best described as a function of how the same algorithm behaves on input n-1. And that sets up a recursive relation. Okay, here is an example. It a little bit looks ahead. We will eventually talk about algorithms and recursive algorithms. If you're very new to algorithms, then you might be quite a handful to take. Here is a famous algorithm, merge sort, that takes a list and sorts elements in it, and sorts much faster than by pairwise comparison of all elements and reordering that way. Because if you have n elements and you try to do pairwise comparisons, then you have n square operations. So if your n is a billion, n square would be, I don't know what, but billion of billions, right? So that's too much. What does merge sort do instead? It's a beautiful case of a recursion, which works like this. Divide a list to sort into two halves, left half and a right half. Assume for simplicity that it's exact, it's an even number of elements. Patch it up if it's not. And run the merge sort algorithm recursively to sort the left half of the list and the right half separately. And you're like, well, what's the chicken and an egg? Hey, you didn't tell me how you do the sort, so how come you can invoke the algorithm? Well, you can. This code is going to generate to its own code, but on a half the list, only the left half. This one will do the same with the right half. And let's assume for a second that this call returns with the correctly ordered left side of the list. Okay, so I took my list. It's a mess. It's completely unordered, but I split it in the middle, and I asked merge sort me the left half, and it did. And sort me the right half, and it did. Now I have two sorted lists. It turns out that it's very easy to merge two sorted lists because, let's say these are the two lists, right? You just go from left to right on both, and you compare the, say this is the smallest. You compare the two smallest elements. Which one is smaller? This one you put on your list. and you increase the index. Every time you output something on your list, you increase the index. And then you again compare these two. Which one is smaller? Let's say this one. So you put that one as next and you increase this index. How many comparisons do you do? As many as there are indices on this list. So it's actually linear. If this list has n elements and this one has n elements, the most number of comparisons you do, every comparison you make, you put someone out. So you perform 2n comparisons. So that's great because it's linear. If you have a billion elements in your list that took billion operations, okay, you cannot expect less. And that's, yes. So now, okay, so if I make the recursive call like this, I make the next time, okay, I split this billion-sized list into 500 million and 500 million. This guy is called on a 500 million number, so it again is going to split it into two halves, for $250 million and $250 million, etc., etc. Eventually, though, it gets into tiny lists. And for those, if the list you called with is actually has only one element, or perhaps even 0 element, because when it was divided, it didn't exactly divide. So one of these lists actually ended up empty. Then that's a very simple. This is the base case of our algorithm. It just returns the list itself, which in this case it's an empty list, and in this case is a singleton. So that's very easy to sort. In either case, you just return the list itself. We'll see in a little bit how to argue that algorithms are correct. Well, okay. In fact, okay. And but let's see first. This algorithm is correct. It will sort every list. Let's see about its running time. That f of n be the running time of this algorithm in the case L has n elements. And now observe that f of n is a recurrence relation. In the base case, where n, the list length, was either 0 or 1, then by the base case of this code, the code basically does nothing. It just returns back the list. So the time of the code is essentially like 0. Okay, the code just didn't do anything. It just returns the input. So let's say I'm measuring running times in terms of the number of comparisons, of integer comparisons between elements. Let's say elements of the list are integers. These code perform no comparisons. So the number of comparisons is 0 in both cases. What about recurrence relation? So what about n greater than 1? In that case, the recursive call will come in. And what will it do? It will perform merge sort on a list that has half of the n elements and a list that has also half. But you know, we have to like do ceiling on one and floor on the other. And what's the time that the merge sort takes? Well, it is defined. It is a value of the sequence, of the same f sequence, at an index that is equal to this. So basically half of this index. Okay, just forget about the floor and ceiling. They're just the noise. So this is the value of the function at half the index. And this is the value of the same function at the same place, half the index. In addition, however many comparisons were performed in this call and in this call, which is expressed here and here, you also had comparisons at the end. But as I was arguing, the number of comparisons here is linear. It's just n. Technically, it's n minus 1. Okay, but again, that's noise. Okay, so this is a recurrence relation. it's no more complex than the recurrence relations we have just seen. And it describes the running time of this. It's not so easy to come up with an algorithm that sorts in general in better than pairwise comparison. And this is an incredibly elegant algorithm. Its description, it's very concise. It's easy to argue that this algorithm is actually correct. As every recurrence relation, it takes a pause. Why is it formed like this? Okay, but you cannot, fail to see the simplicity and the sort of conciseness of it. So this is a very powerful tool, and a recurrence relation is a way to describe its very important properties, like the running time. In fact, as I said, this floor and ceiling is kind of a noise. So so is this one. Let's just simplify it like this: f of n is 2f at half the index plus n. This really is a good enough approximation to what goes on here. And you can ask, well, okay, so what is it? Like if I instantiate it for a billion, this is 2 times, this is a billion plus 2 times f at half a billion. And so I recursively compute this. Okay, f at half a billion is 2 times f at 225 million plus half a billion, etc., etc. I can, but remember, we had a case like this, because this sequence, a few slides back, basically can be approximated as this. The nth value of the sequence is about the value of the sequence at half the index plus 1. What goes on in here is, pretty similar. But instead of incrementing every time, I actually add the index, and I don't take this value plainly, I multiply by 2. We will see later. You can convince yourself this is true, but you can also see later in a next lecture, you have a tool which is induction for how to argue that indeed this expression, the closed formula for it, is a logarithm. You see, the fact that these chunks of equal value grew by a size of 2 every time. So you had 2 2s, but 4 3s, and then 8 4s, and then 16 5s, and then 32 6s, etc. This grows exactly like an integer approximation to a logarithm. And so the closed formula for this is, it's an integer approximation to a logarithm. What about this? Well, actually, this recursive relation, this is a good approximation to it. Okay, it's not an exact thing because it behaves funny when n is not exactly a power of 2, but this is all noise. Essential behavior is like this. It might surprise you that a recurrence relation like this effectively describes logarithms, whereas if I make a tiny change, I just take twice of this, and then another change here, I have a related but a different function. Which of these moves was important? If I had this, but I had only one here, where would I be? Like here or like here? These are, you will learn how to handle these questions. Why? Because they have direct relation to analysis of algorithms. okay, and to understanding how, you know, small code, what kind of behavior can you expect of it? Okay, so let's go back to Fibonacci sequence. Okay, this was all a plugin for an example of a recursive algorithm and how the sequences we have seen and new ones describe its behavior. Another example is biological systems. In fact, the Fibonacci sequence came from a biological system in a way. Fibonacci posed the following problem. You have a bunch of rabbits, and if they are 1 month old, they're too young to replicate. But after that, every pair of rabbits will get together and create an offspring. And so he just approximated like this. Every pair produces another pair, but only, and that's every month happens, but only if they are 2 months old. This means that at a time n, you have everybody from a previous time period, but also you have new ones. But how many new ones? Well, everybody two periods back is old enough to replicate. So that's the number of new batches that you get at period n. That's the source of his formula. And you can ask, okay, so you have this very simple recursive behavior, and you can ask, okay, how big should I expect this rabbit colony to be after 100 months? Should be like quadratic in 100, exponential in 100, or for example, I can ask, okay, if I want 1,000 rabbits, how long do I have to wait? For each of these questions, you can, of course, compute it by hand, right? Like just run this algorithm in your hand, compute consecutive sequence, and just see, you know, what is f of 100, or what's the smallest n, such that f of n reaches 1,000. Okay, but you also might be nice to have a closed formula for this recurrent relation. Turns out there is a closed formula, and it's this one. And when I said that the formula looks complex, well, you can now see that, yes, indeed, a closed formula for this looks complex. Again, what is a closed formula? The point is that this value can be evaluated. It makes no references to any other elements of function of sequence f. The only thing you need is the index n. And once you're given this index, you compute. By the way, Fibonacci sequence has only integers. Here, you know, you see a non-integer terms, but yet for every integer value n, these terms simplify, and the result of this expression is always an integer. Again, you can, one question, how do I verify that this is indeed the formula? Induction will be a tool that will allow you to prove that this is a closed formula for a Fibonacci sequence. Second question, okay, if somebody gives me the closed formula, I can now use induction to verify it. But how do I know? You know, how do I come up with these formulas? That's the end of the of chapter 8. We'll get there. Okay, some famous sequences. Geometric sequence. You define so famous recurrence relations. Geometric sequence is a recurrence relation. You define the first term, and you define every next as some constant ratio times the previous one. Okay, the geometric relation, because you evaluate this, and what happens is the next guy is always r times the previous one. So this guy is r times a. The next guy is r times that, which is r squared times a. The next guy is r times that, which is r cubed times a, etc. This is called geometric sequence, and you see from this that, well, okay, it's an easy guess. What's the general formula, closed formula? It's r to the n times a, and it's an easy exercise by induction to prove that this is correct, that this recurrence relation indeed defines this this closed formula correctly characterizes the sequence defined using a recurrence relation like this. Some geometric sequence, okay, so let's say you start at 5 and your ratio is 2. So every time you multiply by 2, okay, starting from 5, this would be your sequence. If your ratio is smaller than 1, then you're just getting smaller and smaller numbers, right, as you multiply them. If your ratio is negative, then you get an alternating sequence. Let's say, and ratio is -1. So from 2 multiplied by -1 is -2, but you multiply by -1 again, so you get back to 2, etc. If you have some sequence and you can say, okay, let's hypothesize that it's a geometric sequence. What would be the proof of this? Well, test is next guy always defined as some constant ratio times the previous guy. In other words, is G1 over G0 the same as G2 over G1, and is it the same as G3 over G2, etc. And it is, in this case, the ratio is 3, right? So it takes 3 to multiply, right? The next guy is 3 times the previous one. Okay, and we haven't started 4. So the common questions are like, what makes this sequence increasing, decreasing, constant? But you have to memorize them. They're pretty, if you parse them, you will see. I mean, the constant is a particularly obvious one, right? If r is 1, then you get constant, because gn is just equal to gn minus 1. And so if you start at 0, then doesn't matter what r is, you got a sequence of zeros. And everything in between gives you some conditions. Another very common case of recursion, arithmetic sequence. You start from some place, call it A, and then the next element in sequence is defined as the previous one plus some constant offset. Compared to the geometric relation, the next element in sequence is defined as the previous times some constant ratio. And here the is defined in terms of the previous plus some constant offset. Okay, so how does it behave? Well, you're just adding d every time. So you know, the next guy is a plus d, and the next guy is that plus d, so it's 2d, and the next guy is whatever that was plus 1 more d, so it's 3d plus a, right, etc. So the closed formula, kind of immediately see, it's n times d plus a, right? And again, you can prove this by induction. So let's say you start at 5 and your ratio is 2, your offset is 2. You just go add 2 to each number, right? Let's say you add minus 0.1, right? So you're going to arithmetic sequence like this. You're going to have negative offset, so you will be just subtracting, right? You're adding -1, in other words, subtracting 1 at every step. You have some formula. You can test, is it an arithmetic sequence? Is h1 minus h0 the same as h2 minus h1? And is that the same as h3 minus h2? Right, and it happens to be so. The difference is 5. It's plus 5 every time. Okay, these conditions are rather straightforward. Let's move on. Summations. If you have a sequence, you can define a sort of higher level construct, a summation over the sequence. The summation has this sigma sign. It's a Greek letter. It's read summation of sequence terms aj, starting at the bottom, we say where the index j starts at s, and at top where we say where it ends. So this is read summation over aj terms where j ranges starting from s all the way to t. And what that stands for, it's this following sum. I take aj term starting at j equal s, meaning s term. Then the next value is aj terms at the s at j incremented. It was s at first, now it becomes s plus 1, etc. All the way the last index is t. So it's simply this sum of elements. So a summation, you define the beginning and end of the summation, and you are summing over all the sequence elements in the between these ranges. You can also have infinite summations, right? You don't tell where it ends. This expression stands for sum of all sequence elements starting from the s index to infinity. You're going to say, well, maybe this is an infinite thing, so it should be infinite value. Well, not necessarily, because these values could be decreasing. They could be even 0 at some point from some point on, in which case this would be finite. But also, for example, geometric sequence, for some ratio, the values will be smaller and smaller. Perhaps even if I sum infinite amount of them, they're so tiny that they always stay below. I can this will define integer value. Okay. No, it's not for all sequences, but for some. So suppose that I have a closed formula for a sequence. So for example, I have a quadratic sequence like this. The kth element in the sequence is k squared. And then I say, okay, I want to give what is the summation over this over the terms of the sequence from third to sixth. So this simply stands for a third, a4, a5, and a6 all summed up. There is a closed formula for what ak stands for. So this a3 is simply 3 square. A4 is 4 square, A5 is 5 square, A6 is 6 square. So is this, which is that. Suppose that here is another case of a closed formula. So the kth element in sequence is almost like the previous one, but instead of k squared, it's 1 plus k squared. Okay, well, I do the same approach as before, right? This is still true. This summation stands for the sum of the 4 consecutive values of the sequence. But now I have a different closed formula. So a third is 4 square, a4 is 5 square, a5 is 6 square, and a6 is 7 square. Well, maybe I should add here that these two sequences are, it's the same sequence up to a change of variable, right? This AK sequence, let's call it the first AK sequence, and this is the second AK sequence. The second AK sequence, its terms can be described in terms of the first AK sequence. This one would be a value of the sequence, but at the index k+1, right? Because here we will have k+1 square, which is what we have here, right? So it's the same sequence, but just shifted one to the right. So that might be very useful, the change of variable in a sequence, when we have to argue about, well, you're summing over one sequence, but then subtracting some other one. Okay, but maybe it's the same sequence shifted, so you can, this whole subtraction is actually simplifies. Suppose now I can use summation to define a new sequence. Okay, bear with me. Consider the following term. I have some well-defined sequence, and now I'm looking at summations of values of that sequence, ranging from some fixed index, let's say 3, to an index which is a variable, n. So the value of this will depend on n, right? And let me just denote this value as Sn. This is now a new sequence, which is defined in terms of summations over the original sequence. Okay, so for example, this particular case, right? It is Sn is a summation over AK from third to nth element. So it's these kind of sums, and therefore, because this is the closed formula for AK, it's a sum of squares from 3 to n. And there is some closed formula that expresses that number. We can express this as a closed formula. I'm not going to give this to you right now. I will give you some closed formula for some summations of some sequences, and but a summation over squares is a good formula to remember. It's in the book. Okay, maybe I will also get to it, but I'm taking my time. I'm not sure. So summations are really recurrence relation. So, okay, you have this sequence AK, and you are defining the summation. Sn is a summation sequence, meaning Sn is a sum of AKs from first to n. And I can this is a closed formula for what Sn is, but I can also define the same sequence Sn using the following recursive relation. The first element of sequence S is, how do I define it? Well, this way, it's simply A1, because a summation of all AK elements from k equal 1 to k equal n, which is 1, in other words, I range from 1 to 1, is simply, well, there's only one element in the summation, is A1. So S1 is simply A1. Recursive rule is that Sn is the previous element of the sequence, Sn-1, plus An. This is a recurrence relation that defines Sn. Why is that? Okay, what is Sn? It's the sum of all elements of A from first to n. So it's this. But I can group the first n-1 of them. And what is this stuff? It's this, it's Sn-1. So here is the proof. I mean, right? This closed formula, I can look at this if I envelope it, and I notice that the first n-1 elements define the previous element of the sequence, namely this one. Then if I want to, I can look at this as a case of a recurrence, this recurrence relation. Okay. So summations are nothing else than these type of recurrence relations. Now, what about okay, so here is my closed formula for the summation of sequence elements, which are a sequence of squares. So AK is K square. If I sum squares from first to nth, so it's 1, 2 square, 3 square, 4 square, all the way to n square. This is the closed formula for it. It's a third degree polynomial in n. So it grows like n cubed. So the sum of first n squares is roughly grows like n cubed. But it has some other terms, right? So the highest term here is n times 2n, which is 2n cubed, divided by 6. So it's n cubed over 3. But there is other terms, right? We will use induction to prove that this closed formula. And we will look at this summation as a case of the following recursion. The first element is 1, because this summation for n equal 1 just goes from k equal 1 to k equal 1 over values that look like k square. So the only thing is k equal 1, for which its k square is 1. And what about the next values, where they can be defined recursively as all the values so far, all the summation so far, and what's the new one value that I'm adding at nth step? It's n square, right? So this formula, this closed formula, is a closed form of the following recurrence relation, which is also a closed form of the following summation, because this summation and this recurrence relation is an identical thing, just looked in two different ways. Here is so this is one famous sequence and a summation and its closed formula. Here is another one, geometric sequence, right? It's the recurrence relation for a geometric sequence like this. The closed formula is like that, and now we can ask, okay, I want to sum over geometric sequence. I want to sum over its first n terms. What are the first n terms of this geometric sequence? It's a, the next one is RA, the next one are square A, etc. So it's NA times 1 plus R squared plus R to the n. Turns out this summation has a closed formula like this. As you can see, everything here is multiplied by A, so this A stands in front. But the interesting part is, what's the sum? 1 plus R squared plus the result to Rn, and it's this. So for example, if you start at 1, so A is 1, so we can kick it out. And let's say R is 2. So I'm looking at the sum of powers of 2, right? So if R is 2 and A is 1, then this geometric formula is just powers of 2. 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, etc. If I sum over them, let's plug it in here. It's R to the n plus 1, R is 2, minus 1, and I divide over 2 minus 1, which is 1. So therefore, this just vanishes. And so the formula is just the nominator. Is this true, that the sum of the first n powers of 2 is equal to the next power of 2 minus 1? Well, you can easily convince yourself so. Move this to the left side. This becomes 2. 2 plus 2, therefore, becomes second power of 2. But here, the next term is the second power. Second power plus second power is twice second power, which is third power. The next guy is the third power of 2, but you have now third power twice, so it's a fourth power, etc. So therefore, at the end of this reasoning, you're going to get the n plus first power. Yeah. For when R is smaller than 1, you can see that this you can look at the infinite powers, infinite sequence, summation over infinite, where n is equal to infinity, because the r square, r to the terms will decrease, and in going to infinity, this will become 0, and this is minus 1. And let's say you take r 1/2. So this, if n is infinity, then 1/2 to infinity is basically 0. This is minus 1 over 1/2 minus 1, which is minus 1/2. So it's minus 1 over minus 1/2, so it's 2. So what are the, if you instantiate with r equal 1/2 and a 0, what are its, the first term is 1/2 to the 0th power, which is 1. Then the next is 1/2. Then the next is 1/4. Next is 1/8. And you're adding them up, it sums to 2. And you can convince yourself in basically the same way that the consecutive powers of 1/2 sum to 2. For an arithmetic formula, summation over arithmetic formula, it's a simple formula that you probably know, right? So let's say the arithmetic sequence has the closed formula nd plus a. So d is offset, a is the starting point. If I sum the first n such elements, the first one is a, then d plus a, 2d plus a, nd plus a. Of course, the a things, just I can put them outside. And how many terms of them here? I have n. So I have n times a. The rest is the d part. So there's d, 2d, 3d, and then all the way to nd. D is a multiplicative factor. It can come out. So inside there, you have 1, 2, 3, all the way to n. That sum, 1 plus 2 plus 3 plus 4 plus 5 plus to n, the closed formula for this is this. It's almost n squared minus 2 over 2. But it's not exactly n squared, it's n times n minus 1. So this is the most important case of this formula, right? Why? Hold on a second. I'm sort of staring at this, and I don't know myself why I have this n here. I think it's a typo. I don't understand why I have this n. hold on a second. Why do I have this n here? Well, because I guess a is 1, but if a is 1, I can think of this sequence as starting from a1 and adding 1 every time, so d is 1, and so this d here will be 1. And but how many elements I'm adding? Okay. You know what? Hold on a second. I think I'm off already here, because if hn is nd plus a, then hk is not a. Hk is, sorry, h with k equal 1 would be d plus a. So I would be already here and not here. So here I'm summing from k equals 0. So this case. So this is where I have a typo. This should be 0. And yes, so okay, sorry, I have a typo here, and okay, so I have to fix the slide, but the you know, don't look at the black stuff. Okay, the sum of the first n terms is this, okay? And I know there's something funny in this. I mean, you're getting this value if you instantiate a equal 1 and d equal 1. Then, you know, you getting this. And I mean, okay, so fine. So yeah, so just take this formula with a equal 1 and the d equal 1. Then this would be true, right? This becomes here and this becomes here. And if you want to put it in a common denominator, then this becomes 2n, right? So in the denominator, I have n squared minus 2n, but then I have n squared minus n, but then I have 2n from here. So that minus n becomes plus n. So I get this. Okay, this is a little fast, but you can verify these arithmetics. And this is a formula you should remember. The sum of the first integers is n times n plus 1 over 2. And it's a special case of the summation. And the only thing that I have to correct on the slide is kick out value. Okay, this guy is not here. All right, everything else is fine, actually. All right. This is another example of, so this, you're responsible for remembering the summation of an arithmetic sequence and for knowing that the first n integer summed is this. You are also responsible for this arithmetic sequence summation and, you know, understanding its consequences, like for example this, or the one I sketched, that for r equal 1/2, this becomes a 2. The full formula like this, you see, this a is a noise, because if you just remember the same formula for a equal 1, then you can derive immediately for yourself what happens when you multiply by a, right? Because it's just the same formula multiplied by a. Okay, so that's not worth remembering. The part that is worth remembering is set a to 1 and just look at this sequence, and summation over that is this expression. Okay, same in the case of arithmetic sequence, both D and A are sort of noise. Okay, this part is easy to rederive. What's important is actually this: the sum of the first n elements has this formula. Okay, because from that alone you can derive what this is. Multiply this thing by D, and then add some trivial term that has A in it. So, okay, oh, sorry, I'm running over, but I will just do 2 more slides. It is important to be able to relate summation formulas. So, for example, one thing that can be helpful is the understanding like this, that if you have a summation formula that you're summing over a sequence from sum k to sum n, you can split the summation into 2. You can sum over a case from the first one to some arbitrary midpoint of your choice, and then separately go sum over the same formula from that midpoint plus 1 to the end, right? This is just the sum of the terms from first to t. This is the sum from t plus 1 to n. So therefore, altogether is the sum of all terms from 1 to n. So one example we have already seen, the recursive notion of this summation, that the summation up to nth term is the summation up to n minus first plus the last. But also you can see that, okay, if you are asked, what is the summation of some formula from some s point to n, you can represent it as the difference between summation from first to n minus from first to s minus 1, because if you move this thing to the left side, then you have a case like that, right? So why is this important? Because let's say this is some sequence that you know how to compute a closed form expression for summation, but you know how to compute it only if you started from the first term. For example, using the formula for arithmetic sequence, or a formula for a geometric sequence. They start from the first element, right? They both this one and the other one started from the first. How do I use it to sum, let's say, sum of squares, but starting from not first square, but from like 10th square, right? Well, I can, because I use the closed formula here for all squares starting from the 10, and then I use the same closed formula to subtract out the first s minus 1, which is this. And I have the same closed formula for this, but now it will be a closed formula where n is s minus 1, right? So that's how you would use this manipulation. An example of how you would use it. And another thing is a change of terms. Okay, so say that you are summing over some sequence of that from s to nth element, but the values that you're summing are defined as sequences of elements of sequence A at indexes that are with some offset. So that might be complex and unpleasant. Okay, maybe instead you move that offset. You express your sequence terms in a more simple way as I element of a sequence. I equals k plus d. And therefore, if k started as s, then I must start at s plus d, right? Because I is k plus d, and the first k is s. So the first I is s plus d. If I is k plus d and the last k is n, then the last I is n plus d. So therefore, this sequence can be rewritten this way, and perhaps it's nice because you have easier to this is a easier closed formula, or a closed formula that you recognize, or a closed formula for which you know some expression. And this change of variable, where I'm just changing the index here from I to k, this is for free, right? Because this is just a name of a variable. It's arbitrary. It is called I here. It can be called k. It doesn't matter. Okay. So, for example, we had this expressions a few times early on the slide. If you wanted to evaluate close, what is this summation? Well, then you can recognize, okay, this is really the same as adding elements of the k-square function at a shifted index. So rather than start from index 1 and then end at index n, let's start at index shifted by 5, so it's 6, and end at shifted by 5, so it's n plus 5. It's a case of this move. Okay, and now I can use the trick from the last slide. I can represent the summation as starting from 1 to the end, and then subtracting away the first 5 terms. Why? Because I have a closed formula for this. Closed formula is that if I'm ending at n, the closed formula is n times n plus 2 times 2n plus 2n. Okay, forget this closed formula. It's a few slides down. Oh, okay, here it is. Sorry, 2n plus 1. And if my n is n plus 5, then then these terms become n plus 5, n plus 6, and twice n plus 5, which is 2n plus 10, plus 1, so it's 2n plus 11. And I divide by 6, right? And here I just use this formula with n equal 5. So I have 5 times 6 times 11. And boom, I have now a closed formula for this thing. Yes? Okay. So sorry to go over. Thanks for everybody who hanged on. And that's all I have. I'll stop recording, and if you have some questions, you can